Welcome to AI Paper Slop, the YouTube series, where we summarize the latest AI and tech papers for researchers and ML engineers. We are jumping straight in today.
Absolutely no time to waste.
Right. So today's paper is called Breaking Entropy Bounds, Accelerating RL Training via MTP with Rejection Sampling. It's a brand new one from the Quinn team at Alibaba. And honestly, this is a massive operational breakthrough for anyone running reinforcement learning pipelines for large language models.
Yeah, it really targets a massive pain point. I mean, if you are doing RL with LLM, something like GRPO or PPO, you know that rollout generation is your primary compute bottleneck.
Exactly. Multi-token prediction, or MTP, is supposed to be the obvious speculative decoding fix for that, but the acceptance rate absolutely crashes during RL training.
Which is incredibly frustrating. And the core insight from this paper, the thing that changes everything, is why that crash happens.
Right, because everyone just assumed the policy weights were updating and leaving the frozen draft model behind. But the Quinn team proves that's actually wrong. The weight mismatch is negligible. The real problem is that the policy model's entropy is rising because it's exploring.
Yes. And to fix this, they introduced a system called Bebop. It completely swaps out greedy sampling for rejection sampling.
And it replaces standard cross-entropy training with a totally novel end-to-end total variation loss.
Yeah.
The results are just wild, up to 95% token acceptance rates.
A 1.8x end-to-end acceleration in asynchronous RL training for Quinn 3.7 models.
And my favorite part, it completely eliminates the need to update your MTP weights online during RL. So let's unpack this. If you're managing infrastructure for large-scale RL pipelines, you already know the pain.
Oh, absolutely. You have these standard loops, right? Rollout, reward calculation, policy update. We lean so heavily on asynchronous frameworks to hide the latency of the reward and update steps.
Right. You use partial rollouts. You try to hide the bubble overhead from those annoying long-tail trajectories.
Yeah, but those are just tricks. They just mask the underlying reality. And that reality is that the rollout generation stage is just the undisputed wall clock bottleneck. Generating thousands of tokens sequentially just throttles how fast your policy can learn.
Which is why the industry looked at MTP as the savior. You augment your autoregressive LLM with these lightweight draft heads. They predict multiple future tokens sequentially, and then your massive target model verifies them all in a single forward pass.
Classic speculative decoding. It looks amazing on paper.
But the reality is a nightmare. The phenomenon driving ML engineers crazy is the degradation over time. The paper shows that at MTP step 1, the acceptance rate drops by 1.2% as RL progresses.
And by step 3, it's dropping by 3.5%.
Right, which sounds small, but if you are trying to verify 4 or 5 tokens at a time, a drop at step 3 compounds multiplicatively. It completely tanks your overall expected acceptance length.
Exactly. And the conventional wisdom always blamed distribution mismatch for this.
Right. The logic was that the LLM backbone weights are constantly updating via GRPO to maximize rewards.
Yeah.
But your draft heads are just sitting there, totally frozen.
Yeah, holding on to whatever representations they learned back during SFT. The assumption was that the target model is literally drifting away into a new behavioral space.
Rendering the draft model totally obsolete. But, I mean, I have to push back on that premise a bit. Like, wait, if the model is literally updating its weights to learn new behaviors during RL, shouldn't the frozen draft model naturally become obsolete?
Well, that's what makes the Quinn team's decomposition analysis so brilliant. They didn't just accept that premise, they isolated the mismatch effect from the other mathematical factors.
And what did they find?
Looking at data across Quinn 3.5, 3.6, and 3.7 models, the distribution mismatch effect from weight updates is actually negligible.
Wow. So the real culprit is just entropy.
Exactly. To encourage exploration, RL policies have to actively maintain or even increase their entropy.
Right. They need to try out new reasoning paths to discover higher rewards. So let's talk about how entropy mathematically breaks standard sampling. Standard MTP uses target-only or greedy sampling.
Which is highly sensitive.
Yeah. I usually think of greedy sampling like a strict bouncer at an exclusive club. If the draft model doesn't guess the absolute #1 VIP token, the bouncer rejects it entirely.
That's a fun analogy, but mathematically we need to look at what entropy does to the probabilities.
Okay, so imagine throwing darts at a bullseye. The draft model is your aim. If you train the draft model perfectly, your aim is dead center. But what happens when the target model's entropy increases?
The probability mass spreads out.
Exactly. The bullseye physically stretches out and flattens across the entire dartboard.
Yeah.
Your aim hasn't changed. You are still throwing dead center.
But the absolute maximum thickness of that center spot has shrunk drastically.
Because the material is just spread everywhere else. How does the math actually describe this?
So with target-only sampling, the acceptance rate is fundamentally determined by the target model's maximum probability for the top token. Mathematically, it's the max over y of p of y.
Right.
So high entropy just means high uncertainty. The probability mass is forcibly distributed across the whole vocabulary. If we use Jensen's inequality, we can actually formalize this.
Okay, lay it on me.
It shows that the expected maximum probability is lower bounded by the exponential of the negative entropy.
So in simpler terms, as entropy goes up, the mathematical ceiling for acceptance comes crashing down.
Precisely. It doesn't even matter if your draft model perfectly predicts the target model's top choice. The target model itself is just less confident about that top choice.
So the overall probability of acceptance drops linearly. The draft isn't wrong, the target ceiling is just lowered.
Right, exactly. So if target-only sampling is fundamentally brittle to the entropy of the target model, we need a sampling method that evaluates the throw differently, to use your dartboard analogy.
Which brings us to the massive pivot in this paper. Since greedy sampling is broken by entropy, they shift to probabilistic rejection sampling.
And rejection sampling completely rewrites the criteria for acceptance.
How so? Because it doesn't just look at the top greedy choice anymore.
No, it looks at the entire distributional overlap. It measures the total variation, or TV, distance between the draft distribution and the target distribution.
Oh, I see. So you're evaluating the draft model on its overall shape across the vocabulary, not just its top guess.
Exactly. And that is why it survives the entropy stretching effect.
Because even if the target model is exploring and its entropy is super high, maybe the absolute top one token flips back and forth. Like maybe it's deciding between the word therefore and thus.
Right, very similar tokens.
But with rejection sampling, even if that top token flips, the overall area under the probability curves of the draft and the target remains largely overlapping.
You aren't penalized for a slight re-ranking of the top tokens. You still guarantee an unbiased output, but you don't tank your acceptance rate just because the target was feeling a little uncertain.
That is huge. And the paper highlights that rejection sampling outperforms target-only sampling almost universally for native MTP models.
Yeah, the decision boundary they map out is actually very simple. Rejection sampling wins whenever the draft target TV distance is smaller than the target probability mass that falls outside the draft's greedy prediction.
Meaning, whenever the target model pushes a lot of mass into the long tail due to high entropy, rejection sampling is just mathematically superior.
Universally better, yes.
But, and this is a big but, just dropping rejection sampling into your pipeline doesn't magically fix everything?
No, it doesn't, because the paper identifies a massive underlying flaw in how we actually train these MTP models in the first place.
Right, the standard objective functions.
Yeah.
Cross-entropy loss or KL divergence. It turns out they are actually suboptimal for rejection sampling.
They actively work against it. When you train a draft model with cross-entropy, the gradient applies pressure uniformly across the entire vocabulary.
Uniform mismatch.
Yeah.
Right. It distributes the optimization effort based on the absolute difference between the draft and target, but it doesn't care about the actual magnitude of the target probability.
Exactly. It's a uniform mismatch penalty.
So let me give an analogy for what that does to the model's compute capacity. Say my vocabulary have 100,000 tokens. The target model decides the word banana has a 0.001% chance of being the next token in a Python script.
Which is just noise.
Right, it's total noise. But because cross-entropy applies uniform pressure, my draft model wastes its finite optimization capacity trying to get its own prediction for banana down from 0.00002% to 0.00001%.
It's obsessing over completely irrelevant long-tail tokens.
And when entropy is high, that long tail is super thick. So these uniform per token errors accumulate into a massive total variation distance.
Which drags down the acceptance rate. You need a probability proportional mismatch, not a uniform one.
And that is where the Quinn team introduces their fix. The end-to-end total variation loss.
Yes, the E2E TV loss. Instead of cross-entropy, this novel loss function directly optimizes the total variation distance itself.
And it does it end-to-end across multiple MTP steps simultaneously. I like to think of it this way. Cross-entropy is a student wasting all night memorizing the entire dictionary just in case a random word shows up on a test.
Analogy.
But TV loss is the student who only studies the exact material that will be on the final exam. But I do have a technical concern here.
Okay, what is it?
Doesn't TV loss run the risk of zero forcing? Like, if it ignores the long tail entirely, what happens if the target model suddenly shifts its behavior during RL and decides a low probability token is actually the right one? Doesn't the draft model blind itself?
That's a very valid concern, but that zero forcing behavior is actually what happens if you try to use reverse KL divergence as your objective function.
Oh, because reverse KL drops modes of the target distribution.
Exactly. Reverse KL is mode seeking, which would blind the draft model. But the TV loss avoids this by using a selective indicator function.
How does that work?
Its gradient is proportional to the draft probability itself, which they denote as Q sub j.
So it scales the gradient based on what the draft thinks. How does that prevent zero forcing?
It acts as an automatic self-correcting mechanism. It drives the ratio of the draft to target probability toward 1.
Ah, I get it.
Yeah, so if the draft probability is lower than the target, the gradient pushes it up. But because the gradient magnitude is proportional to Q sub j, it naturally scales down to 0 for tokens, where both the draft and the target agree the probability is near 0.
So it doesn't artificially force those tokens to 0. It just stops wasting compute on them once they are safely in the noise threshold.
Exactly, and naturally ignores them. This creates a draft distribution that is incredibly sharp and perfectly aligned with the target's high probability peaks.
And because it's end-to-end across multiple steps, it naturally weights earlier steps more heavily, perfectly capturing the multi-step verification process. This leads us to what I think is the most insane operational payoff of this whole paper.
The pre-RL adaptation hack.
Yes, because E2E TV loss makes the draft model virtually invariant to entropy shifts, and because weight mismatch is negligible under rejection sampling, you get a massive gift for your infrastructure.
You absolutely do not need to update your MTT weights during the online RL loop.
You can just leave them completely frozen. Think about the hardware implications for you as an engineer. Online MTP updating introduces severe memory overhead. You have to maintain optimizer states for all those draft heads.
The momentums, the variances, all of it.
Plus the computational latency of backpropagating through them during every single RL step. By proving the draft model is robust to target shifts, the Quinn team gives you permission to just drop all of that overhead.
It's so elegant. You just perform a lightweight one-time pre-RL MTP training phase during your supervised fine-tuning stage.
Using the E2E TV loss, of course.
Right. And that one-time adaptation provides stable, high acceptance rates throughout the entire downstream RL training run.
No matter how much the policy model explores or updates, but there is a huge danger here if people try to fall back on old habits.
Oh, absolutely. The paper highlights a fascinating empirical finding. If you start with this beautifully sharp TV-trained draft model from your SFT phase, but you mistakenly decide to leave online MTP updates turned on during RL.
And you use standard cross-entropy laws for those updates.
The acceptance rate actually degrades right back down to the terrible CE baseline.
Wow. Because the CE loss starts smoothing out the perfectly sharp draft distribution you just spent SFT building.
Exactly. It forces the model to start caring about the long tail again, actively destroying the total variation overlap. So truly, just freeze the weights.
Just freeze them. So let's talk about where this Bebop system actually shines in production. They test it across reasoning, math, and software engineering workloads.
And the agentic and SWE tasks saw the absolute biggest gains, up to an 8% higher acceptance rate, hitting 98% or more overall.
Why do you think SWE tasks see such a massive boost?
It comes down to the structure of those tasks. Agentic tasks have massive contexts, up to 128K tokens. They have high entropy exploration when reasoning through complex code, but they also contain highly predictable structural boilerplate.
Oh, like JSON formatting, strict tool call syntax, XML tags.
Exactly. And a TV loss-trained MTP model perfectly exploits that structure. It completely ignores the noise of the long tail, so it just blitzes through the structural boilerplate with near 100% acceptance.
The massive speed up on predictable tokens perfectly offsets the slightly slower verification on the high entropy reasoning tokens,
yielding an incredibly fast overall rollout.
This also solves the temperature scaling dilemma for engineers. If you crank up the temperature to force RL exploration, standard target-only sampling completely crashes.
Because you are artificially inflating the entropy.
Right. But under rejection sampling with TV loss, the acceptance rate stays completely flat and robust. You can turn up the heat without doubling your rollout latency.
So, for the engineers listening, let's talk implementation. The paper outlines 2 specific production implementations depending on your serving engine.
Because rejection sampling requires you to draw from a residual distribution if a token is rejected, which is tricky on a GPU.
Very tricky. If you are using SGLang, they use multinomial draft sampling. This involves caching the full draft probability vectors and using explicit CDF inversion.
Cumulative distribution function inversion for the residual resampling.
Right.
But if you're using VLLM, explicit CDF inversion is a total nightmare for memory. Building a CDF requires sequential summation across the entire vocabulary dimension, which destroys GPU parallelism.
Yeah, you don't want to do that. So for VLLM, they use the Gumbel max trick specifically to avoid explicit CDF inversion.
Oh, right. So you can stay in logit space.
Exactly. Instead of converting logits to probabilities and sequentially summing them, you just add Gumbel noise directly to the temperature-scaled logits during the draft state.
And you cache those.
Yep. Then, during verification, if a token gets rejected, a parallel kernel computes the residual distribution entirely in logit space.
By applying the same Gumbel noise and taking the argmax, that is a brilliant bypass. You draw an unbiased sample without ever instantiating the full CDF in memory.
It really is. And we should also mention the memory costs of computing the TV loss itself during that pre-RL adaptation phase.
Right, because engineers love to cut corners by approximating vocabulary-wide loss functions with top K truncation.
But the authors noted that even keeping a massive K value of 20,000 causes severe loss spikes and training instability.
You cannot cheat the TV loss. It requires the full vocabulary.
Yeah, so to do that efficiently without blowing up your VRAM, you absolutely need full vocabulary fused kernels. The fused backward kernel bounds the register and shared memory usage by tiling the vocabulary computation,
Which allows the GPU to compute the full gradient without ever materializing the massive softmax output tensors in high bandwidth memory.
It's essential.
So we've covered a lot. The mystery of degrading MTP, the elegance of rejection sampling, the necessity of TV loss, and the massive savings of dropping online updates. I want to leave everyone with a broader implication to chew on.
Sounds good.
If the Quinn team just proved that draft models can be made entirely robust to the policy model's entropy and weight shifts simply by utilizing E2E TV loss and rejection sampling, what does this mean for the future of inference time compute?
It's a paradigm shift.
It really is. Historically, draft models needed to be heavily co-trained and perfectly synced with the exploring reasoning models. But if they no longer need to be tightly coupled, we might be entering an era of massive decoupling.
We could see a future where specialized, static, TV-trained draft models serve as universal plug-and-play accelerators.
Exactly. Universal draft models for highly dynamic RL agents. It could fundamentally lower the cost of scaling reasoning at test time. You don't always need to change your aim when the target gets blurry. Sometimes you just need a better mathematical framework for evaluating the throw.
A perfect way to look at it.
Well, that's all for today's deep dive into the Bebop system. Thanks for joining us on AI Paper Slop, and we'll see you next time.